All right, question 1 is calculator based. I don't have a mechanism right now to show you my calculator, but hopefully we'll be able to muddle through it and figure it out. We've got a velocity function, right, that applies between 0 and 5. And then we have the position at time 0 being x equals 8. Part A says find the acceleration of the particle at time 4. So my work for part A, if I'm going to find acceleration at time 4, that's going to be equal to the derivative of velocity at time 4. So I'm going to write that down, but I don't actually have to calculate that by hand. So what I'm going to do instead is just use the Math 8 feature in my calculator and go ahead and type that in, ddx of that v function, and then in the box we're going to do an x equals 4, and then your calculator will tell you 0.714. You could also take this derivative by hand using the chain rule, and you would get 5/7 as your exact answer that way. Part B says find all times t in the interval where the particle changes direction, during which time interval 0 to 5 does the particle travel to the left. So particles change direction where velocity changes sign. So we're going to take this velocity function and set it equal to 0. Now, the only time an ln function is equal to 0, right? Like ln of 1 equals 0, right? So technically, we need t squared minus 3t plus 3 to be equal to 1, and that would be the solution for some critical numbers. So with that in mind, I'm going to subtract 1 from both sides, and then I'm going to factor this correctly, I hope. Nope, not correctly. Oh, that's a 2, sorry. Dum. Minus 2. How about? Okay, and then that gives us answers of 1 and 2. And then I'm going to go ahead and kind of make a sign chart between 0 and 5 for the sign of my velocity function to see where it changes sign. So with that in mind, I can just plug in numbers to the actual velocity function. So to test this point here, I'm just going to figure out what z of like 0.5 is, right? So probably in my calculator, I'm going to put that function into y1 and then just look at a series of signs. Or like I'm going to go to the table and just type in different values. So at 0.5, the v function itself is positive. At v of 1.5, when I type that in my table, I get negative. And if I try like v of 3, I get another positive answer. So since I have these two sign changes, we're going to say it changes direction at 1 and 2. And then it also asks us during what interval does a particle travel to the left. So let's put this information together. Particle, well, here. Let's put it on by where this graph is, or the sign chart. Particle changes direction. At t equals 1 and t equals 2, because v of t changes sign. And then because I know I'm going to run out of room here, I'm going to answer this question up here in the pink, right? The particle travels to the left from 1 to 2. Particle travels left on 1 to 2. Because velocity is negative. Okay, so that kind of addresses both parts. Part C says find the position of the particle at time 2. So I know that I have this point on the position function like 0, 8. That's 1 point on it, and then I'm trying to figure out 2, I don't know what. So I'm going to use the fundamental theorem to help me with this, because I'm going to think of this as A and this as B, and I'm going to solve for f of B. So f of 2 is equal to that initial condition of 8 plus the integral from 0 to 2 of the velocity function. You are not going to work that out by hand, right? This portion you're going to use Math 9 to do. All right, and when you total up 8 plus that integral, we actually get 8.368. Or if you round it, I assume we get 8.369. So that's all the work that it takes. Again, I'm thinking of this formula that we had kind of studied in this unit. F of A plus the integral from from A to B of little f. Okay, so think that little f and big F in the formula have the same relationship between velocity and acceleration, or velocity and position, right? Because position is the antiderivative of velocity, and big F is the antiderivative of little f, so that works out. All right, and then let's see, maybe part D, do a little color change here. Find the average speed of the particle over the interval 0 to 2. Okay, so this is fun because we have never studied average speed. This would be a question that they're just kind of throwing at you to see, can you take the ideas of what you know speed is represented by and the ideas about what averaging means to do, and then put all that together to try to calculate an average speed. So they give us this interval 0 to 2, so that of course means very likely that we're going to be using integration. So we're going to integrate from 0 to 2, and to average it out, we're going to put 1/2 in here. But I'm not going to do average, right? This would be average velocity, right? And that's actually not what I'm being asked to calculate. What I'm being asked to calculate is average speed. Okay, so I'm just going to leave this here so you can kind of compare and contrast. So average speed means that we would include absolute value marks around velocity, because remember, that's the relationship. Speed is non-directional and velocity is, so speed is the absolute value of velocity. And then I would type that into my calculator using the absolute value feature. Okay, go slow, make sure you remember the 1/2 in front. That gets forgotten a lot of times. So I would use Math 9, and you would come up with 0.370, and then if you round, 0.371. Okay. Moving on to the next one here, we've got Karen taking her bike for a ride. So she's on a straight road. Okay, one path from her home to school. Isn't that convenient? Starting at time 0, traveling to time 12. And during that interval, her velocity is pictured up above here. Okay, so we know that time is in minutes. And I think, right, this is miles, probably miles per minute here. Okay. Part A says, find the acceleration of Karen's bicycle at time t equals 7.5. So since we're looking at a graph of velocity, to find acceleration at that moment, we have to know the relationship between velocity and acceleration. Turns out that they are, one is the derivative of the other, right? So at time 7.5, we're talking about that red dot on the function. So really, I just need the slope of that line right there. And since it's linear, I can use this point here, which is 7, 0.3, and this little point here, which is 8, 0.2, and I can calculate the slope between those two to give me my answer to part A. So again, we've got to be really good about showing our work. So let's say 0.2 minus 0.3 all over 8 minus 7, and that would give us negative 0.1 divided by 1, so it's negative 0.1, and then it says indicate units of measure. So since I've calculated acceleration, that's going to be miles per minute squared. Okay, which is, remember, it's okay, I guess, to write, if it makes more sense to you, you can write miles per minute, if you like it that way. Part B. Using correct units, explain the meaning of 0 to 12 with the absolute value marks around V of t and Karen's trip, and then find the value of that. So 0 to 12 with the absolute value marks, we're calculating total distance traveled is the total distance traveled. God, I never remember if that's 1L or 2. By Karen over 12 minutes. It's important to say it is measured in miles because it says including units. Right, and then to calculate that actual number, right, we're going to do greens, all this area underneath this curve. So, let's see. So the two green triangles at the first part kind of cancel each other out. So I'm actually just going to count what I see here left over. This is kind of an annoying portion to calculate here. So let's see. This first green triangle, I've got 1/2 base of 1, height of 3. So, ooh, it's not a height of 3. That's crazy. It's a height of 0.3. So we have 0.3 over 2 for the first green triangle. Then we have 3 boxes here. So remember that's 0.3. And then we have basically 2.5 boxes. Which, I don't know, which is annoying, I guess, to come up with in terms of decimals. So 0.1, 0.2, and then another half of that. So I've got 0.25 for the, next to that, this like kind of trapezoidy looking thing. Okay, and then let's see, I've got 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 for the next. Let's make it this purple region here. Right, so remember that's worth 0.6. And then the last thing in the orange here would be 1/2 base is 1, but height is 0.2. This is hideous. So probably I would just put this exact summation right here without totaling it. I would put that for my answer in part B. And I would just say that, the integral from 0 to 12 under this guy equals that expression. Again, you do not have to simplify it on the AP test. So that's one saving grace. All right, part C. Shortly after leaving home, Karen realizes she left her calculus homework at home. Who would do that? And she returns to get it. At what time does she turn to go back home? Give a reason for your answer. So it looks like she turns around at 2 because her velocity changes signs. Right, so she was traveling to the right or forward, however you want to think of it, and then she turned around and started traveling left or backwards, however you want to think of that sign change. Okay. And then D. Larry, good buddy Larry, also rides his bicycle along a straight road from home to school in 12 minutes. His velocity is modeled by that function. W is miles per minute. Who lives closer, Karen or Larry? So I think what we have to do is compare those are their velocities. So we have to compare, I think, their displacements. Right, we have Karen's wonky total up there in the circle. So Karen's distance from home, we excluded the part where she left and then turned around and went home. So at time 5, is when I think to time 12 we can count how far she lives from school. And since her velocity was positive that whole time, that would count as her distance from school. So I'm going to be a total cheat and like turn this into a number really quick for us to talk about using my calculator, which I know is breaking the rules, but since I didn't work it out ahead of time, I don't want to say the wrong thing. Okay, so I think that is 1.4 for her distance in that summation up above, miles from school. And then we have to calculate Lair Bear, his, I think, again, total, his displacement, which would be 0 to 12 of pi over 15 sine of pi equals t. Oh, maybe this is a I think this is a calculator question now that I think of it. So we wouldn't have to do that integral by hand. I actually can't remember, but let's just let's type it in using Math 9 anyway, and disregard the part where I said no calculator. So we get 1.6 miles for this calculation. So then I think we could say Karen lives closer to school. Okay, showed all my work, justified why I said the things I said, right? And that's pretty decent. So let's say you can use the calculator on this.